dioxide, the ore from which iron to be extracted, is concentrated by roasting or calcination so that water gets eliminated as vapor. Carbonates get decomposed to release carbon dioxide, and sulfide gets oxidized to sulfur dioxide. This concentrated ore is mixed with limestone and coke and sent into a blast furnace to reduce the metal oxide to the metal. Here, coke reduces ferrous oxide to iron, releasing carbon dioxide, as shown in the equation here. This is a combination of two simple reactions. In the first reaction, ferrous oxide gets reduced to iron. Let the change in the Gibbs free energy for this reaction be delta G, FeO, Fe. In the second reaction, carbon gets oxidized to carbon monoxide. Let the change in the Gibbs free energy be delta G, CO. When the two reactions occur, the net Gibbs energy change becomes delta G reaction is equal to delta G CO plus delta G FeO Fe. This becomes spontaneous when delta G reaction is negative. Ellingham diagrams are useful in predicting the conditions under which a metal ore can be reduced to the metal. It gives information to predict the equilibrium temperature between the metal oxide and the metal. If a graph is plotted for standard Gibbs energy change delta G naught against temperature in Kelvin scale, capital T for both these reactions, then it will go upwards for the reduction of ferrous oxide to iron, FeO, Fe, and downwards for the oxidation of carbon to carbon monoxide, CO. From the graph, you can see that at a temperature above 1073 Kelvin, carbon reduces iron oxide to iron, but itself undergoes oxidation to form carbon monoxide. Thus, the carbon monoxide oxidation line crosses the iron oxide iron reduction line and then remains below it. Let us apply this concept to the extraction of iron in a blast furnace. In the furnace, iron oxide is reduced at different temperatures. Iron oxide ore is introduced into the furnace from the top. At the same time, coke is burnt in the lower portion of the furnace, blowing hot air to produce a temperature of 2200 Kelvin. When the coke burns, it produces carbon monoxide and the heat required for the process. The heat produced moves upwards along with the carbon monoxide. The temperature at the top of furnace is lower, and hence iron oxides like Fe3O4 and Fe2O3 get reduced to FeO in different stages. This corresponds to the intersection points in the curves which we just discussed. Let us now see how iron oxides get reduced to iron in different temperature ranges. Between 500 and 800 Kelvin, carbon monoxide reduces iron oxides, as shown here. Carbon monoxide acts as a reducing agent since it has a lower negative delta G naught value for the oxidation of carbon monoxide to carbon dioxide than for the oxidation or carbon to carbon monoxide. Thus, in a blast furnace, hematite is reduced by carbon monoxide even though carbon is mixed with it. The equation for this reaction is Fe2O3 plus 3CO gives 2Fe plus 3CO2. In the temperature range of 900 to 1500 Kelvin, carbon monoxide reduces ferrous oxide to iron, as shown here. Silica is an impurity. Limestone removes it in the form of molten slag, which is taken out from the bottom of the furnace. The molten iron obtained in this process contains 4% carbon, along with some other impurities like sulfur and phosphorus. It is called pig iron. Pig iron is melted with scrap iron and coke in the presence of hot air to form cast iron, which contains only 3% carbon. It is hard but brittle. Cast iron is heated in a reverberatory furnace lined with hematite, which oxidizes carbon to carbon monoxide to get wrought iron or malleable iron, the purest form of iron. In this process, limestone is added to remove impurities in the form of slag. The metal is removed and separated from the slag by passing it through rollers. Copper occurs in combined state as sulfides, oxides and carbonates. Copper pyrites or chalcopyrites and copper glands are its sulfide ore. Cuprite is its oxide ore, while malachite and azurite are its carbonate ores. Now look at the Gibbs energy versus temperature plot for the formation of oxides. You can see that the line for cuprous oxide is almost at the top, while the lines corresponding to the formation of carbon monoxide and carbon dioxide from carbon are much lower, particularly after 500 to 600 Kelvin. Therefore, it is quite easy to reduce cuprous oxide to copper by heating with coke. However, most ores of copper are sulfide ores, and some of them may contain iron. Hence, the sulfide ores are first roasted or smelted to give oxides. The oxides are then reduced to metallic copper using coke. In practice, the concentrated sulfide ore containing iron as an impurity is mixed with silica and heated in a reverberatory furnace. During this process, most of the iron sulfide is converted into its oxide, which further reacts with silica to form a fusible slag of iron silicate. Copper is produced in the form of copper matte, which contains copper sulfide and iron sulfide. The molten matte is now introduced into a converter provided with a lining of silica. A blast of sand and hot air is blown into it. During this process, the remaining iron is removed in the form of slag, while copper sulfide is reduced to metallic copper. The metallic copper then melts and sinks to the bottom of the converter. This molten copper is poured into molds. When the molten mass is allowed to cool down, SO2 gas escapes. As a consequence, the copper so obtained has a blistered appearance. Hence, the product is called blister copper. Blister copper contains 98% copper and is refined through electrolysis. Now let us look at the extraction of zinc. Zinc occurs widely in nature in the form of sulfide, oxide, and carbonate ores. Zinc blende is its sulfide ore, zincite its oxide ore, and calamine is its carbonate ore. as can be seen from the Ellingham diagram. The reduction of zinc oxide to zinc occurs at a higher temperature than that required for the reduction of copper oxide to copper. Coke is used for the reduction of zinc oxide. Depending on whether sulfide or carbonate ores used for the extraction, the concentrated ore is either roasted or calcined. The zinc oxide obtained after roasting or calcination is reduced to zinc in vertical retorts. In practice, zinc oxide is powdered, mixed with coke and clay, and then made into small briquettes. The briquettes are placed in vertical retorts that are lined internally with clay bricks. Producer gas is used as the fuel to heat the charge. At high temperatures of 1400 to 1500 degrees Celsius, coke reduces zinc oxide to zinc and itself gets oxidized to carbon monoxide. The zinc metal is distilled off and collected by rapid chilling. The zinc obtained is 97% pure and is called zinc spelter. The principles of metallurgy are effective in the reduction of metal ions to their respective metals in their solution or molten states. Here, the reduction is carried out through electrolysis or with the help of other reducing elements. Such methods are based on electrochemical principles. These electrochemical principles are explained in the equation shown here. Delta G naught is equal to minus N E naught F. Here, N is the number of electrons gained, and E naught is the electrode potential of the redox couple. The value of E naught for a metal depends on its reactivity. Thus, it differs from metal to metal. More reactive metals have high E naught values, whereas less reactive metals have low E naught values. It is difficult to reduce metals that have high E naught values. If the difference between the E naught values of two metals is positive, then the value of delta G naught will be negative. Hence, the less reactive metal will come out of the solution and the more reactive metal will go into the solution. For example, the reduction of copper plus 2 to copper in the presence of iron. The corresponding equation is shown here. In a simple electrolysis process, the positive ions always move towards the negative electrode, called the cathode. For every electrolysis process, we need to take some precautions. Consider the reactivity of the metal produced in the electrolysis. Use suitable material as the electrodes. Sometimes, flux is needed to increase the conductivity of the molten mass. The metallurgy of aluminium is the best example of reduction of metals through electrolysis. In this process, we add cryolite and fluorspar as flux to aluminium oxide. Because pure aluminium oxide is a bad conductor of heat and electricity, the fused substance is used as the electrolyte. The entire cell reaction is shown here. In this process, the electrolyte is taken in a steel container lined with carbon, which acts as the cathode. A bunch of graphite rods immersed in the electrolyte act as the anode. This process is also known as the Hall-Héroult process. When current is passed, all the Al+3 ions move towards the cathode. Oxygen is liberated at the anode, which reacts with the carbon atoms of the anode to form carbon monoxide and carbon dioxide. Finally, the anode will be burned away. In this way, for every kilogram of aluminium produced, about half a kilogram of carbon will burn away at the cathode. The cell reactions are shown here. The extraction of copper from low-grade ores or scraps is the best example of reduction of metals with the help of other reducing agents. Generally, copper is extracted from its low-concentrated ores by a process known as hydrometallurgy. In this process, a solution containing Cu+2 ions is treated with a scrap of iron or hydrogen, as shown here in the equation. You have already studied how metals are extracted from their ores by the process of reduction. You know that non-metals are generally available in combined states in their reduced forms. Hence, non-metals are isolated or extracted by oxidizing their compounds. For example, chlorine is isolated by oxidizing brine solution. Since oxidation cannot be carried out by normal chemical methods, chlorine is extracted by electrolysis. The chemical reaction corresponding to the electrolysis is shown here. The delta G naught for this reaction is plus 422 kilojoules. The minimum potential difference needed for oxidation, E naught, is equal to minus 2.2 volts. Due to overvoltage, the electrolysis process requires an external EMF greater than 2.2 volts. In the process, chlorine gas liberates at the anode. Hydrogen and sodium hydroxide are the byproducts. The electrolysis of molten sodium chloride also produces chlorine gas at the anode and sodium metal is deposited at the cathode. Let us now see how metals are extracted by both oxidation and reduction. You have already studied that of gold and silver are extracted by leaching their ores by cyanide ions. During the leaching process, silver and gold are treated with sodium or potassium cyanide in the presence of air to form the respective soluble complexes. In the process, silver is oxidized to silver plus 1 and gold to gold plus 1. The next step is the recovery of the metals from their respective complexes by reduction or displacement using zinc. In this process, zinc acts as a reducing agent. A metal extracted from its ore by any method is generally impure and is known as crude metal. The impure metal is purified by subjecting it to a process of purification or refining. Depending upon the nature of the metal and the impurity present, various refining methods such as distillation, liquation, electrolysis, zone refining, vapor phase refining, and chromatography are used. Let's look at each one of these techniques in detail. First, let us study distillation. This process is used to purify metals with low boiling points, such as zinc, cadmium, and mercury. In this method, the impure metal is heated in a retort and its vapors are separately condensed in a receiver. The pure metal distills over, leaving behind the non-volatile impurities in the retort. Let's look at another refining method, liquation. This method is used when the impurity is less fusible than the metal itself. In this technique, an impure metal with a low melting point, such as tin or lead, is heated at just enough temperature to melt it using a sloping hearth. The impurities with higher melting points do not melt and stay at the top of the sloping surface, while the molten metal flows down, thereby separating it from the impurities. Another important refining method is electrolysis. In this method, the impure metal is made the anode and a strip of the same metal in its pure form is made the cathode. An aqueous solution containing a soluble salt of the same metal is used as the electrolyte. On passing electricity, pure metal is deposited on the cathode. The more basic impurities go into the solution, while the insoluble impurities, particularly the less basic ones, settle at the bottom of the anode as anode mud. For example, copper is refined by the process of electrolytic refining. Impure copper metal is made the anode, while a thin strip of pure copper strip is made the cathode. An acidified solution of copper sulfate is taken as the electrolyte. On passing electricity, copper atoms from the impure copper anode lose electrons to become Cu2 plus ions and enter the electrolyte. These metal ions are reduced at the cathode and are deposited as pure metal. The more electropositive impurities like iron, nickel, and zinc are left in the electrolyte as their sulfates, while the less electropositive impurities like gold, silver, and antimony settle at the bottom of the anode as anode mud. Precious metals like gold and silver can be recovered from the anode mud. Other metals like silver, zinc, lead are also purified by this method. Let's now study the zone refining technique. This technique is based on the principle that impurities are more soluble when the metal is in its molten state than when it is in its solid state. This technique is used for obtaining metal with very high purity. The process is carried out in an inert atmosphere to prevent the metal from getting oxidized. In this technique, a movable circular heating roller is fixed at one end of a rod of impure metal. The metal melts in zones, called molten zones, as the roller moves towards the other end of the rod. When the heating roller shifts forward, the metal to the left cools down and crystallizes, while the impurities dissolve in the molten zone. In this way, the impurities keep shifting along with the molten zone to the right, and pure crystallized metal is obtained on the left. The process is repeated several times till the impurities are completely removed. Elements such as germanium, silicon, and gallium, which are used as semiconductors, are refined by this method. In another refining technique, which is vapor phase refining, the impure metal is first converted into its volatile compound. The volatile compound is then decomposed to give pure metal. It is essential for this technique that the volatile compound of the metal should be easily formed and easily decomposed. Let us consider nickel. Nickel reacts with carbon monoxide to form a volatile nickel tetracarbonyl complex at a temperature of 330 to 350 Kelvin. The nickel tetracarbonyl is then heated to 450 to 470 Kelvin, where it decomposes to give pure nickel and carbon monoxide. This method is known as Mons process for refining nickel. Another example of vapor phase refining is the Van Arkel-de Boer method for the purification of titanium and zirconium. In this method, titanium or zirconium, which contain oxygen and nitrogen as impurities, are heated in an evacuated vessel with iodine to form the volatile titanium tetraiodide or zirconium tetraiodide. The metal iodide is then decomposed on a white-hot tungsten filament at 1800 Kelvin to give the pure metal. Now let's move on to the last refining technique, chromatographic methods. In these methods, the metals and the impurities are separated by the difference in their relative adsorption with an adsorbing medium. The mixture to be separated is applied onto a stationary phase. And a mobile phase is allowed to run slowly over the stationary phase. The components in the mixture get partitioned between the mobile phase and the stationary phase, and thus get separated. Depending upon the physical state of the mobile phase and the stationary phase, and also on the passage of the mobile phase, different chromatographic methods, such as paper chromatography, column chromatography, and gas chromatography are used. Let us take a look at column chromatography, which is particularly useful for the purification of elements that are available in minute quantities, and the chemical properties of the impurities are not much different than that of the element to be purified. In this method, alumina or silica gel is packed in a column and serves as the stationary phase. The mixture to be separated is placed on the top of the column. A suitable eluent is allowed to flow down the column slowly. Depending upon the degree to which the components in the mixture are adsorbed, complete separation takes place. Let us now study the uses of some commercially important metals, such as aluminium, copper, zinc, and iron. Aluminium foils are used as wrappers for chocolates, medicines, and food items. Aluminium dust is used in paints and lacquers. Since aluminium is more reactive than chromium and manganese, it is used in the extraction of these elements from their oxides. Aluminium is used to make electrical wires as it is a very good conductor of electricity. Aluminium alloys are light and are very useful. For example, gamma alloy and duralumin, which are alloys of aluminium, are used for making aeroplane parts. Copper is used for making electrical wires. Copper pipes are used in homes and industries to carry water and steam. Copper forms alloys such as brass with zinc, bronze with tin, and coinage with nickel. These alloys are harder than copper and have many domestic and commercial uses. Zinc is used for galvanizing iron. Galvanized iron does not corrode and is used to make pipes, roofs, I-beams, fences, and wires. Zinc is extensively used in carbon-zinc dry cells or batteries. Zinc forms alloys such as brass with copper and German silver with copper and nickel. Brass is used in musical instruments, doorknobs, and ornaments, while German silver is used to make silver-plated cutlery, idols, and jewelry. Zinc dust is used as a reducing agent in the manufacture of dye stuffs and paints. Cast iron, the most important form of iron, is used for casting stoves, railway sleepers, toys, and gutter pipes. It is also used in the manufacture of wrought iron and steel. Wrought iron has several uses. To name a few, it is used to make anchors, wires, gates, bolts, chains, agricultural equipment, and furniture. An important alloy of iron is steel, which has many domestic and industrial uses. Different varieties of steel can be obtained by adding other metals like nickel, chromium, cobalt, and manganese to it. For example, nickel steels, which have varying amounts of iron and nickel, are resistant to wear and tear and can withstand mechanical shock. Hence, nickel steels are used for making cables, automobile, aeroplane parts, pendulums, and measuring tapes. Similarly, chromium steels, which are extremely hard and resistant to wear, oxidation, and corrosion, are used in armor plates, cutting tools, crushing machines, and stainless steel for cycles, automobiles, utensils, pens, cutlery, and surgical instruments.